All right, today we're jumping into the molecules that literally power our world and build so much of the stuff around us. We're talking about hydrocarbons.
So think about this for a second. What are the gasoline that gets you to work, the plastic in your water bottle, and the natural gas that might be heating your home? What do they all have in common?
The answer, believe it or not, is actually pretty simple. They are all hydrocarbons. Yep, these incredible, diverse materials are all built from just two of the most common elements in the universe.
But how in the world can just two elements create so much variety? Well, that question takes us straight into what we can call carbon's astonishing universe, where we're going to see exactly why this one element is the undisputed superstar of the molecular world.
So what's carbon's secret sauce? What's its superpower? Well, it's this. A single carbon atom can form up to 4 incredibly strong and stable bonds, especially with other carbon atoms. This unique talent makes it the ultimate molecular Lego brick. You can use it to build these long chains, complex branches, and even perfect rings. So just how many different molecules can you build with this carbon Lego? You might want to brace yourself for this one. The estimated number of potential organic compounds is 10 to the 60th power. That's a 1 followed by 60 zeros. I mean, that number is just beyond astronomical, and it really shows you how insanely versatile this one little element is.
And you know, the simplest of all these organic compounds are the hydrocarbons. The name kind of gives it away, right? They're molecules made up of only hydrogen and carbon atoms. But as we're about to see, simple definitely does not mean boring, not even close. So let's start with the most basic family of hydrocarbons. Welcome to the saturated world of alkanes.
Alkanes are what we call saturated hydrocarbons, and saturated just means that every carbon atom is holding on to the absolute maximum number of hydrogen atoms it possibly can. It's totally full. This happens because all the bonds between the carbon atoms are single bonds, and that makes these molecules incredibly stable and sturdy. Now, to actually visualize these things, chemists have a few tricks up their sleeve. Let's take pentane as an example. First up, you've got the expanded formula. You can see every single atom and every single bond. It's perfectly clear, but man, it takes forever to draw.
So, to clean that up a bit, there's the condensed formula. Here, the hydrogens are just grouped together with the carbon they're attached to. It's the same exact structure, just with fewer lines to worry about.
And finally, we have the skeletal structure, which is how most organic chemists actually do it. Each point or end of a line is a carbon atom, and the hydrogens are just implied. It's the ultimate shorthand. It's fast, it's clean, and it's elegant.
Now here's where things get really fascinating. You can have the exact same chemical formula, but create totally different molecules. Take C4H10. You can arrange it as N-butane, a simple straight chain. Or you can snap those same pieces together a different way and get 2-methylpropane, which has a branched structure. Same parts, different assembly. These are called structural isomers, and that difference in shape gives them completely different properties.
So how complex can this get? Well, an alkane with just 18 carbon atoms has, wait for it, over 60,000 possible structural isomers. That's 60,523 different molecules from the exact same set of atoms. It is just mind-boggling. Okay, so far we've only seen single bonds. But what happens when carbon atoms start sharing more electrons? Well, that's when things get a whole lot more interesting. Let's enter the world of the unsaturated and reactive. We're talking double and triple bonds. So here's the key difference. Those saturated alkanes with their sturdy single bonds are pretty stable. But alkenes are unsaturated because they have at least one double bond. Now, you can think of that double bond as having a weaker, more exposed part that's just begging to be broken. And that little weak spot makes alkenes far more reactive.
And this reactivity is actually incredibly useful. We can take these small individual alkene units, we call them monomers, and use that reactive double bond to link them all together, kind of like snapping beads onto a string. This process is called polymerization, and it creates a long, strong chain. In this case, it makes polyethylene. Yep, the tough, flexible plastic used in everything from milk jugs to grocery bags.
So if a double bond makes a molecule reactive, what do you think a triple bond does? You guessed it. Alkynes, which have a carbon-carbon triple bond, are even more reactive than alkenes. The simplest one, acetylene, is so reactive that its combustion produces the incredibly hot flame used in welding torches. All right, now it's time for a very special class of hydrocarbons. Let's dive into the aromatic ring, and specifically the king of this category, benzene. Benzene is this really neat 6-carbon ring, but its bonding is, well, it's unique. The electrons in its double bonds aren't locked into one spot. Instead, they're delocalized, which is a fancy way of saying they're shared equally by all 6 carbons in the ring. They just zoom around the whole thing. This constant sharing creates this powerful, stable structure, making the molecule incredibly resilient.
And because that benzene ring is so super stable, it's used as a foundational piece for countless other chemicals. Chemists can just swap out a few hydrogen atoms to create vital industrial solvents like toluene and xylene. Or they can make styrene, which is the monomer used to produce polystyrene, the stuff we all know as styrofoam.
So, we've seen the incredible variety of these molecules, but where do we actually get them from? Well, our final section brings this whole story full circle. We're going from crude oil to you.
The main source of hydrocarbons is crude oil, and you can think of it as just a complex soup of all these different molecules mixed together. To separate them, we use a process called fractional distillation. Basically, the crude oil is heated until it vaporizes. Then, these hot vapors rise up a tall tower and start to cool. Different hydrocarbons condense back into liquids at different temperatures based on their size. The lighter molecules, like gasoline, make it all the way to the cool top, while the heavier ones, like diesel oil, condense much lower down.
And this all brings us back to that one core idea that makes everything we've talked about possible. This quote from our source material says it perfectly. It's all because carbon atoms can form up to 4 strong bonds to other carbon atoms, and that's what results in these chains and rings of every imaginable size, shape, and complexity.
And that's why this matters. Hydrocarbons are the ultimate molecular building blocks. They're at the center of everything from fuel to medicine. And it all comes back to carbon's simple but incredibly powerful ability to connect. Which kind of leaves us with one final thought. Given this incredible toolkit, what will we build with it next?